Okay, I'm going to start here. I'm going to work, this is exam, I guess this is the second exam from spring 2022. Okay, so we're going to kind of just walk through this. Excuse me. Okay, so streamlines show the path of, we're going to just kind of go in order, I guess. So streamlines show the path of individual particles in a flow through time. That is false. Streamlines show the tangent line to the velocity vectors at a given time for all points. Okay, the buoyant force on a basketball is the same whether it is fully or partially submerged. This is false, and it's because, the force of buoyancy equals, well, usually it's written as gamma times the volume displaced. Okay, and this is the gamma of the fluid. And of course, if the volume displaced changes, then the buoyant force will change. So if it is fully or partially submerged, there will be less or more displacing fluid. So this is false. Okay, low Reynolds number indicates a turbulent flow. That's false. High Reynolds numbers indicate turbulent flow. The Eulerian point of view refers to a moving reference frame. That's incorrect. This is a Lagrangian point of view. So that's going to be false. And at this point, we're almost looking at a sweep of falses. Mass is conserved in unsteady flow. Mass is always conserved, unless you get into nuclear reactions. So mass is always conserved. Negative gauge pressure means that the fluid will cavitate. No, it does not. I guess it would be a prerequisite for fluid cavitation, but really it needs to be very, very negative. Okay. This is one that, I suppose probably what I'll do with this one might mean, it's definitely false, but I might, give you a point there, just because negative gauge pressure really is required for a fluid to cavitate, but it's not going to cavitate just because it has negative gauge pressure. Okay, the Bernoulli equation assumes the viscosity of the fluid is negligible. That's true. Okay, so basically we always say it's inviscid, or there's no friction basically. Laminar flow is characterized by irregular movement and high momentum exchange within the fluid. That's false. That's kind of what's going on with turbulent flow. For incompressible fluids, volume is conserved. That's true, and the reason for that is because an incompressible fluid. So if you got in equals out plus accumulation. Usually every one of these terms, so that's always mass in, mass out, mass plus acceleration. But usually this is going to be a rho Q. All of my in terms are going to be rho Qs. All of my out terms are going to be rho Qs. And my accumulation is going to be d by dt of rho times the volume. Okay? This is really a summation. If those if the rho is the same everywhere, then it just cancels out. And now I've got volume, then, so these Q's all cancel due to mass conservation. Not due to the incompressibility, and they're all the same. And so what ends up happening is we've got an equation for volume instead of for mass. Okay. And for an object submerged in a fluid, the buoyancy force is equal to the difference in the pressure force on the top and the bottom of the object. That is true. In fact, that is kind of the definition of the buoyancy force. Okay, so here we go. So now we're going to go down here. A 90-degree elbow is yada, yada, yada. So this one I took directly from Connect. So this is C10, number 13 and 14. C10, number 13 and 14. Okay, so this is from your homework. And I think, so that's it. I think one of those two was like in the X direction and one was in the Z direction, but whatever. Or I don't really remember. Anyway, so here we go. So we're gonna draw this sucker. Okay, so we need a free body diagram of this here bend. Okay, so this is of the bend and the water. Okay, so here we go. So this is what it looks like. Okay, or something. Obviously, that's not very good, but whatever, right? It doesn't matter. Okay, so this is a test. We don't have time to overthink this stuff, right? So here's V1, here's V2. Note it's got a constant diameter. Let's see, the 10 centimeter diameter. So this is 10 centimeters here. This is 10 centimeters here. So V1 equals V2. So I could just make the V if I wanted to. The elbow discharges water into the atmosphere. That means that there is no pressure right here. However, there is a pressure right here. Okay, so this is P1A1. Okay, so because we're trying to draw all the forces on this thing. What other forces do we have? Well, let's see here. We've got a weight going down. Okay, that's the weight of the water and the elbow. Okay, so that's going to be a mass times a gravity. I've got an anchoring force in the X, which is probably going to be the opposite direction from that. And then I've got an anchoring force in the Y, or the Z, I suppose. Okay, so I think I've got all my forces, and I've got my 2 momentum fluxes in blue. Okay, so that's everything. All right, now what do we need here? Usually, you know, you guys know me. I like asides. Okay, and maybe we'll get to the asides in a second. Let's go ahead and do the momentum equation, and then we'll kind of see what we need as we work through it. Okay, so the sum of the forces, we want the vertical force, so the sum of the forces in the vertical, plus rho VZQ. Okay, that's usually a summation. These are the ends, equals the summation over the outs of rho VZQ. Okay, so let's see here. The forces in the vertical, I've got the anchoring force. I've got minus the weight. And that's it. Okay, for this in, I don't have an in. I don't have anything in the Z direction, so this is 0. Actually, you know, I should do that in blue if I'm kind of keeping my fluxes in blue. Okay, and so then we'll say, okay, well that equals, okay, so now we'll do the fluxes in blue. So this one's on the way out, so I've got rho V, so the one out is right here, it's positive, so positive, VZ, V2, okay, Q. And that's our whole equation. Now let's see, which of these do we not know yet? Okay, so we know, well, that's what we're looking for. The mass is given, we know gravity. Rho, it's water, so it's 1,000. V2 we don't know, and we don't know Q. Okay, so we know those. We need to know those. Now, one nice thing here is rho Q is m dot, so you know we've already been given that. So we can just plug in 32 kilograms per second, but we still need V. Okay, so let's start here, but we'll say m dot equals rho Q. Okay, so one thing we could say right there is rho Q equals 32 kilograms per second. Okay, so that we could plug that in for rho Q over in that equation on the left if we wanted to. Let's see here, what else are we going to do? Okay, but really, you know, what we want out of that is we want Q, because I need to get velocity, right? Kilograms per second equals rho, which is 1,000 kilograms per cubic meter, times Q. Okay, so if we solve that, let's see here. Let's just make sure we got our units going right. We got kilograms. And so Q is going to be meters cubed per second. So 0.032 meters cubed per second. Okay, unless I've moved my zeros incorrectly. All right, so now we need V2, okay, or we need the V, which is the same everywhere in this problem. So let's see here, Q equals V, I'll call it V2A2, it doesn't matter, because the A's are all the same and the V's are always the same, okay? So Q is 0.032 cubic meters per second equals V2, that's what we're looking for, times A2, which is pi times this diameter, 0.10 meters squared divided by 4, okay? And we'll end up with V2 equals, let's see, this is one of those calculator things. Okay, and I'm getting a number like 4.0744. Okay, and that's meters per second. Okay, so there we go. So now we have everything that we need to plug into this equation. Okay, so we'll go over here and let's see here. So we get FAZ minus the mass of the elbow and the water. It's 10 kilograms. Okay, so we'll go 10 kilograms times 9.81 meters per second squared equals rho, which is 1,000 kilograms per cubic meter, times V2, which is 4.0744 meters per second, times Q, which is 0.032 cubic meters per second. Okay, FAZ then equals, I think if we do the math on this, assuming I didn't make an error when I did this before, 228.48 newtons. And we'll keep 3 sig figs, so I'll make it FAZ equals 228 newtons. Okay, let's see, how did I grade this? Maybe we'll do the grading in red here. I try to keep this fairly simple here, so this is worth +2, +1, +1. That way I could give you a point if you forgot to multiply that by 9.81. This is worth +2, because I ask you guys 10,000 times a class, what is the rho? +2 and +2. Okay? If you put in any extra terms, I'll take a point off. Okay? So like some of you might have had a VN, some of you guys may not have gotten rid of this one. And if you put that in there, then you're going to get a, -1. Of course, that would also, like if you were to put that in, it would completely negate this term right here, because it would be exactly the same number. Anyway, so this one's worth 10 right here. So this is 10 points. This one was worth 10 points. So on this page, there are 20 total. Okay. So moving on, we're going to go down to this one. Let's see, we've got, if D is 14 meters, Q1 is 0.05 cubic meters per second. Q2, well, let's see, we gave you this instead. Let's see, Q2 is, the diameter of the pipe is 0.5 meters, and the flow rate is 0.2 meters per second. Okay. At what rate is the level of the tank increasing or decreasing? Okay. So let's figure this out. Okay, so we've got in equals out plus accumulation. Okay, so I've got row 1 Q1 going in, row Q1 going in, row Q2 going out, and the accumulation is the change of mass through time in that control volume. Okay. Now, since this is an incompressible flow, all those rows are going to go away. Okay, and I'm left with Q1, which is given. So we'll go ahead and go with 0.05 cubic meters per second equals Q2. Let's see here, 0.2 meters per second. So that's the velocity times the area, which is going to be pi times this diameter right here times 0.5 meters squared divided by 4. And then we'll have to go with plus. So this is going to be change in volume with respect to time, but this area on the top is not changing. So the volume equals the area of the top, okay, this area, times the height right here. Okay, so if I wanted dV dt, what I could do is I could pull that area out and I'll get dH dt, right? So that's what I'm going to do. So I've got the area of that top, which is going to be pi times 14 meters squared divided by 4. Okay, and then I'm going to be left with dH dt. Okay, and that's, we'll notice, like, I mean, I don't know, this is really large by comparison to the others, by the other terms. So whatever's going to happen here, this thing's going to be really small, whatever it is. This is a really big tank, and we're draining it with, really tiny, or we're filling it in and raising it with very small numbers. Okay, so I mean, if I do the algebra here, 0.05 cubic meters per second equals, if we do all this, assuming I didn't make a mistake, 0.039270 cubic meters per second. Okay, plus, this is 153.94 meters squared. That's that area times dH dt. Okay, so we can see that more is coming in than is leaving, so it's going to raise. But because the tank is so big, it's not going to raise very quickly. Okay, so dH dt equals, this is a positive number, meaning it's going upwards. Okay, it's increasing. 6.9702 times 10 to the negative fifth meters per second. And if I want 3 sig figs, which I do, dH dt equals 6.97 times 10 to the minus 5 meters per second. That's the rate of it raising. Okay, and that's an increase. Okay, so let's see here. So how did I grade this sucker? I tried to keep this one simple too. So it's going to be plus 2, plus 2, plus 2, plus 2, and plus 2. Okay, so if I just look at this equation right here, that is basically how I'm going to grade it. If you interpreted it incorrectly, then you would lose a point. Or if you forgot to tell me, how you interpreted it, you'll lose a point. So this is going to be 10. Okay, so let's go down here. This one. Okay, let's see. I love Venturis. Oh, wait, hold on a second. This one right here, I think this one just came off of an old test. This is an old test problem. I've used this one several times. Okay, I don't think this is from an old homework or anything. Okay, this one right here, came from C9, number 6. C9, number 6. Okay, so if you want to look at, its take on how to solve this, it's right there. I think that, well, of course they use different numbers for theirs, but that's okay. Okay, okay, so here, I like to do my asides over here. I like to do my main thing over here, okay? Water flows through a horizontal pipe at this annoying rate, okay? So already I know I'm going to have to convert 1.96 gallons per second to, cubic feet per second because I don't want to work in gallons. The pipe consists of 2 sections of diameters 4 inches and 2 inches, okay, with a smooth reducing section. So right here when they say it's smooth, they're trying to push you in the direction of using Bernoulli by saying, hey, look, there's no energy loss between 1 and 2, which, by the way, we need to figure out where those locations are, 1 and 2, which we choose because those two, well, we know the diameter, but also, we have this manometer attached, so we can figure out the pressure difference between these two locations. Okay, so anyway, I'm going to erase that because that's going to kind of get in the way. Anyway, the manometer shown uses mercury, S equals 13.6. Okay, which means, of course, this is water, so S equals 1. Neglecting frictional effects, now they just straight up tell you to do it. Determine the differential height H of the mercury between the 2 pipe sections. Okay, so let's do our main thing over here, and our main equation here is going to be Bernoulli, because, well, they're kind of telling us what they want here. It doesn't have to be Bernoulli, I should say here. Because they're looking for this H right here, you could have made your main equation the manometer equation. One day, maybe I'll try to solve it that way. I mean, there's nothing wrong with doing it that way. I just don't want to rearrange Bernoulli and plug it into something else. I think that's just inviting a disaster. So let's just go ahead and make Bernoulli our main equation. All right, so let's see here. So Z1 and Z2, these are going to go away because they're the same. Okay. P1 and P2, these are going to come from manometer. Okay, right? And V1 and V2, these are going to come from continuity. Okay? So, I haven't graded these yet. I'm about to start. I saw one of you rearrange this equation, and I kind of liked it. There's nothing wrong with doing it this way. So I'm going to do it this way. Okay. Over 2G equals P2 minus P1 over gamma. Okay, and this is a lovely way to do this. And of course, you know that I like this. I like this right here because that's how I like to plug my manometer equation in. And this over here is just a perfectly reasonable way to plug in your velocities. Okay, so, but what this means now is I need to, so I need to get the manometer for this. and I need to get do some continuity for this, right? Okay, so let's go down to my asides, and I'm going to start with continuity over here. The first thing is I got to deal with this 1.96 gallons per second, so I'm going to do that 7.48 gallons per 1 cubic foot. Okay, so that's going to give me a really annoying number, 0.26203 cubic feet per second. No, not per, CFS, sorry. CFS. Okay, and that's okay. I mean, obviously it's an annoying number. We have calculators though. Okay, so now we'll do, let's see here, we'll do continuity. Okay, and I'll say, okay, well, Q equals V1, A1. Okay, and that's going to be for this point right here. Okay, because I have Q. Oh, sorry, this should be Q equals. So I have Q. And I have V1, and I can get A1, right? So Q is 0.26203 CFS equals V1, which is what I'm looking for. And A1, which is pi times the diameter, 4/12 feet divided by, okay, like that. And if I do this, and this is a little bit sad for me, going. Okay, so this is a little sad because it's, because I make y'all keep 5 sig figs until the end. So it's a little bit annoying, 3.0027 feet per second. But again, we have calculator, it's no big deal. Okay, so I could do this again for position 2, for over here. However, you should know at this point from my class that, the ratio of the diameters is a factor of 2. So the ratio of the velocities will be 2 squared, which is 4. So V2 is faster, so it's going to be 4 times faster. So this is going to be 12.011 feet per second. Okay, so there's V1 and V2. Okay, so we'll go ahead and box those off. Okay, so those are going to go in on the left-hand side of the Bernoulli. And now I need to do, and since I have all this space over here, I'll go ahead and use it. I want to do Bernoulli. I mean, not Bernoulli, the manometer. So this is no longer under our sides, but whatever. Okay, manometer. Okay, and let's see here. So I'm going to start at position 1. So I'm going to do P1. I'm going to go down, well, let's see here. We're going to go down some bit. I'll call this bit right here capital H. Okay, because we're not really that worried about it, because we're going to go down in water here, and then we're going to come back in water there. So it's going to go away. So I'll go plus gamma times H plus this lowercase h. Okay, now I'm going to come across, and now I'm going to be coming back up. Minus gamma Hg, that's mercury, times that lowercase h. And then I'm going to come back up, minus gamma water, times that capital H. And then that's going to give me to P2. Okay, so to rearrange this, let's see here. So I'm going to bring the P1 over here by subtracting. And I'm going to divide both sides. Let's see here. And then I'm going to divide both sides by gamma. So I'm going to be left with gamma H plus H minus gamma Hg times lowercase h minus gamma H divided by gamma. Okay? So what's going to happen here is we're going to end up with, let's see here. I'll just keep the P2 minus P1 over gamma over here. And over here, I'm going to end up with H plus H minus gamma Hg over gamma times lowercase h minus h. Wait, I missed something here. No, that's right. Okay, so these capital H's are going to go away. I'm going to be left with, well, what I'm left with, this thing right here, what I'm going to do is I'm going to pull an h out. H, and I'm going to end up with 1 minus, okay, gamma Hg over gamma, which can be written as SHG over gamma water, well, or just gamma, I guess, because I've been calling gamma water gamma, divided by gamma, equals P2 minus P1 over gamma. So this all comes out, and I'll just say it as P2 minus P1 over gamma. These are going to cancel, equals H times 1 minus 13.6. Okay, so P2 minus P1 over gamma equals negative 12.6 H, which is really kind of pretty when you think about it, okay? So let's go, so we'll take that number and we're going to plug it in over here into this equation, negative 12.6. And so we'll get negative 12.6 H equals V1 and V2. So V1 is 3.0027 feet per second. Wait, feet per second? How did I get feet? Is this whole problem is in feet? Yeah, I guess it is. All right. All right, I'll have to check my my other work. All right, anyway, so that's going to be squared minus V2, which is 12.011 feet per second squared, all divided by 2 times gravity, which is 32.2 feet per second squared. Okay? I didn't use anything specific over here, so this still holds. Okay, good. Okay, so if we stare at this, we just need to solve this. And notice those negative signs are going to cancel because this side is going to be negative. And I'm going to get H equals 0.16668. I guess this is feet, although when I solved it, I called it I called it meters, so I'll have to redo that on my key. And you know, I don't really like that, so I'm gonna change that into inches and give myself 3 sig figs. Well, I guess if I wanted to keep it as feet, I would say 0.167 feet, or I would just, you know, multiply that by 12, because I think it comes out nice and clean to say this is, you know, 2.00 inches. Okay. Kind of up to you. I mean, I guess either one of these works. This is nice and clean to me, though. Okay. You know, how often does that happen in you know, fluids to get a clean answer in the what do you call it system we're in? It's just called the silly system we're in. The silly system. Okay. So anyway, so how did I grade this? Basically, okay, so basically it comes down to the things you had to plug in, okay? So if we look at our sides, getting these velocities is worth 2 points. Getting this equation is 2 points, okay? And then knowing what to do with them, okay? So if you got the wrong velocities but you plugged them in over here, that would be okay, because I would still give you 2 points for plugging in an incorrect velocity, okay? And that's it. So that's 10 points for this one. Look, it's 5:30. So maybe we're almost out of here. Okay, so this one, let's see. I got this one from Connect. Okay, this is Connect 9. I think it's what, 8 through 10 or something like that. 8 through 10, something like that. Okay, I made this one a little bit easier than that one. But you know, what do you do? Okay. All right, water at 20 degrees C flows from the reservoir at 1 through the siphon shown and out into the atmosphere at 4. Okay, so here's 1, here's 4. Okay, determine the maximum velocity of the water exiting at 4. So let's do that one first, okay, because that's 7 points. That's where most of the points in this problem are anyway. So let's just go ahead and do it. Okay, so let's, we're just do Bernoulli from 1 to 4. Okay, ideally we would do the energy equation, but, you know, that's not on this exam. So we won't do that. V1 squared on 2G equals P2. And this is easily the purest Bernoulli on this whole test because you don't have to, like, there are no asides here. Okay? So at location 1, let's see here, we'll note that I should really get kind of a uniform thing here. So at locations 1 and 4, I should change that. These should all be 4s, right? 4, 4, 4. Okay, so anyway, so at both of those locations, right here, it's open to the atmosphere. Right there, it's open to the atmosphere. So these are going to go away. Okay. The elevations of these two, that's the most straightforward thing. Okay, the elevation at 1. So I'm going to make this my datum right here. Okay, this bottom line right here, it doesn't have to be the datum, but I'm going to make it the datum. Okay, so we note that at 1, it's, I guess it's 5 meters above the datum, so this will be 5 meters. And at location at 4, that's at the datum, so that's going to go away. And then we note that the velocity at 1, because it is a reservoir, or, you know, we'll use the Tahoe assumption. Okay, and so that one goes away. And then now we're ready to go. Okay, so if we, you know, because V4, well, that's what we're looking for. Okay, so we'll say 5 meters equals V4 squared on 2 times G, which is 9.81 meters per second squared. Okay, so if we solve this equation, we get V4 equals 9.9045 meters per second. And if we, you know, clean that up, we'll get 9.90 meters per second. Okay, so 3 sig figs. Okay, how did I grade this? Let's come in here with red. So I just said, okay, well, this is a point, 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 this is a point. Okay, the answer is 1 point. Okay, so that's your 7 points for that one. You know, I was just looking to, you know, can you know, clean up a nice Bernoulli equation. Okay, so now we're asking for, so now we'll go into the second part of this. If the vapor pressure of water is this annoying number, and we know the atmospheric pressure, okay, H is 10 meters. Okay, will the water cavitate in the pipe when moving at the velocity found in A? Okay, so basically, in that case, we know V4 equals 9.9045 meters per second. You probably don't need, or you almost certainly don't need that sort of precision in these sorts of numbers. But, you know, it is the way that I like things done, so I'm just going to kind of stay there. However, what I want to note is that there's 2 real possible locations for cavitation. One is right here. Okay, and why? It's because Z is very high. Okay, so the higher in elevation you are, generally the lower the pressure you are. The other location is at location 2 because the velocity is very high and the Z is kind of middling, right? Because like the velocity is the same here as it is here, as it is here, as it is here, as it is here, but we want the highest location amongst there in order to check it. So we really need to check 2 locations, 2 and 3, okay, to see, you know, location 2 because it's the highest location with the higher velocity, and location 3 because it's the highest location, period. Okay, so these are the 2 spots we want to check. Okay, 2 and 3. So in order to do 2 and 3, what I'm going to need is I'm going to need to do Bernoulli from 1 to 2, and I'm going to need to do Bernoulli from 1 to 3. I could also work backwards from 4 if I wanted to, but it doesn't matter. I'm going to stay with going from 1 to 2, and from 1 to 2 and from 1 to 3, because 1, the whole side adds up to 5 meters. I mean, technically the whole right-hand side, you know, at V4 also adds up to 5 meters, so it doesn't really matter. But sometimes it's easier for me to think forward rather than backwards, so I'm just going to do that. All right, so I'll do the asides over here. On my key, I did not do them in this order, but that's okay. So I'll do, okay, P1 over gamma plus Z1 plus V1 squared on 2G equals P, we're going to go to 2. 2 over gamma plus Z2 plus V2 squared on 2G. Okay, this whole left-hand side, excuse me, is going to come out to 5 meters because it came out to 5 meters over here. So I'm not really all that worried about it. Okay, P2 on gamma, that's what I want to solve for because I want to know is this thing, you know, pretty sure it's going to be negative. It's going to have a negative pressure, I think. But the real question is it going to be negative enough to cavitate? Okay, so Z1 or Z2 is going to be 2 meters because we got this right here, 2 meters. And I need to know V2 squared on 2G. 2 times 9.81 meters per second squared. Okay, so I'm stuck without V2 right there. And actually, if I'm going to go that far, I might as well put the gamma down here. So this is 98 10 newtons per meter cubed. Okay, so now I'm waiting for V2 squared. Okay, so that shouldn't be too hard. And we'll do that as an aside over here. So I need to get what V2 is. So V2, so I recognize that the flow at 2 is the same as the flow at 4. So V2A2 equals V4A4. Okay, so V2 times A2, which is pi, they gave us the diameter of the little pipe, which is 0.107 meters squared over 4, equals V4, which is given over here, sorry, not given, solved for, 9.9045 meters per second. Okay, times that area, which is going to be pi, times 16 centimeters, 0.16 meters squared over 4. Okay, so V2 equals, so notice V2 is going to be faster. And what did I get for V2 here? I think I got 22.146 meters per second, which is cooking, to say the least. All right. So 22.146. 22.146 meters per second. Okay. Just to give you an idea of, you know, the scale of these numbers, you know, we've got 5 meters equals some P2 over 9810 newtons per meter cubed plus 2 meters. So these two are just elevations. But this this velocity head, I mean, that's a big number. It is almost exactly, and it should be exact if there was no if there were no rounding errors, but I'll leave it as the calculator spits it out. But there is a rounding error that's making that happen, but that's okay. Meters, okay? So that's a huge amount of energy right there. So if we solve for this thing, okay, so there's just a tremendous amount of energy in that velocity. So all this elevation has been converted to a really, really rapid velocity because the pipe is narrow. Okay, and let's kind of figure out what that means. So if we solve this, we're going to get P2 equals, this is going to be a negative number, as it has to be. Okay, so I'm getting 215,790 pascals, or newtons per meter squared. Okay, that's a really, really, really negative number. And just to give you an idea, you know, here's my atmospheric pressure. Okay. So if I wanted, so this, remember, this is all gauge. Okay, so if I wanted to turn that into absolute, I would say, okay, well, P2 then equals, so if I wanted it in absolute, it would be 101,325 pascals minus 215,790 pascals. So P2 is a negative number absolute. I actually didn't do this calculation. I guess I can do it real quick. Negative 114,470 PA. Okay, it's impossible to be absolute, to have a negative velocity in the absolute sense. Okay, so this is certainly below the vapor pressure, so it will certainly vaporize. And in fact, this is impossible. This is fundamentally, like, you can't even get this. You can't even go this low, right? Because you can't go below 0. So this will cavitate under all thermal conditions. So the temperature of the water does not even matter in this case. It will cavitate, okay? Absolutely, completely, no question, and it will cavitate here, okay? And it's probably going to begin cavitation somewhere before it gets there. Now, I don't know where that location is. We could figure that out. It's probably going to begin as soon as it starts flowing at that velocity. We could figure that out. Yeah, it's almost definitely, because if we were to go there, instead of 2 meters right here, we just have 1 meter. It's still going to cavitate there. So, yeah, so don't have a tiny little hose coming out the bottom of a 4 meter deep container. Okay. Anyway, so it will cavitate. However, some of you guys instead are going to try location 3. Ideally, you would have done both. So let's check location 3. Okay, so let's do this again. And I'll say P1 over gamma plus Z1 plus V1 squared on 2G equals P3 on gamma plus Z3 plus V3 squared on 2G. Okay, so location 3 is right there. Okay, remember the whole left-hand side of this is going to be 5 meters. I'm going to get P3 on gamma, which is 9810 newtons per meter cubed. Okay, the Z at 3 is 10 meters. Okay, I tried to get a number that would make this close. I think I succeeded. I can't remember. And then plus, well, V3. What is V3? Well, the diameter of the pipe here is the same as the diameter of the pipe here, so the velocity will be the same. So we'll do 9.9045 meters per second squared divided by 2 times 9.81 meters per second squared. Okay. Again, I want to kind of give you a sense of what these numbers mean, or what the scale of these numbers are. 9810 newtons per meter cubed. We've got some nice clean numbers here. And it should come as no surprise that if I plug this in, this is going to be 5 meters. How do I know that? Well, because look up here, right? I said that this equals 5 meters, right? Okay, so if there were no rounding errors, that's going to be 5 meters. So P3 then, if we solve this, okay, in this case, most of the energy is going to raising, well, maybe not most, I guess half the energy is going to raising it from 5 to 10, and the other half is going to, giving it some velocity. Okay, so the velocity has nowhere near as extreme here as it was in the other one. Okay, so if we solve this, I end up with P3 equals a negative 98. Well, this should be obvious, right? Because it's a 10, so it's a negative 10, so newtons per meter cubed. Okay, now we want to remember newtons per meter squared, excuse me, or pascals. Okay, remember this is gauge. Okay, so I want to turn that into absolute. So I'd say, okay, well, P3 then equals 101.325 kilopascal, or 101.325 kPa minus 98,100 pascals. Okay, so this is going to be if I wanted it in absolute. Okay, so if I do that calculation, it's 3,225 pascals absolute. Okay, and we're going to compare that to the vapor pressure of water, which if I go up here, what's the vapor pressure of water? Looks like it's 2,338. 2,338 pascals absolute. Okay, and that is at a temperature of 20 degrees C. So because P3 is greater than PV, no cavitation. So it will not cavitate at this point, right here, but it will cavitate right here. Okay. So the way that for these 3 points, ideally what I would have done here is I would have said getting this pressure here is 1, and then recognizing that means it's going to cavitate is a +3. I think probably you'll get a point or two for doing this one, but hopefully I hope that you recognize that this was also a danger point. Okay. So anyway, so that's a total of 10 right there. Okay, so there you have it. Hopefully you did well. That's the whole exam, and that's all I got. So hopefully this helps you guys, and I'll see you in class soon. All right, take it easy. Bye.